the Curious Calculator. In today's video, we're going to be going over degrees versus radians. So if you've ever taken a class in trigonometry, you're probably familiar with something that looks like this. This is commonly known as the unit circle. And for someone who's not familiar with this, or you just want a brief review, let's go through this a little bit. So here around the circle we have the different angle measures listed both in degrees and radians. So degrees and radians are two different ways to measure angles. And if we kind of go around this, we notice that, well, right here is 45 degrees, this is 90 degrees, this is 180 degrees, 270, and then all the way around the circle would be 360 degrees. And looking at it in radians, we can see that 45 degrees is equal to pi over 4 radians. 90 degrees is equal to pi over 2 radians. 180 degrees is equal to pi radians. 270 degrees is equal to 3 pi over 2 radians. And the whole circle is 2 pi radians. And the other numbers that you see here are the sines and cosines for the different angles, but don't worry about that right now. We're not going to be getting into that for this video. So at this point, we see that there are two different ways that we can measure angles. One of those is using degrees and the other is using radians. And at this point, you might be wondering, well, why do we even have two different ways to measure angles? And is one of them more beneficial than the other? So that's what we're going to be getting into right now. And in order to do this, I want to begin with a little diagram and talk about the origin of the 360 degree circle. So bear with me for a moment while I kind of draw this diagram, and then we'll get into why I'm doing it. So let's imagine here that we have the sun. So let's say this is the sun right here. And then right here, let's draw a little circle for the earth. And then we're going to draw these arrows to kind of show or represent the revolution of the earth around the sun. And sorry for my drawing skills, they're not the best, as you can see. So let's see here. So the 360 degree circle really began with the Babylonians around 500 BCE. And the reason for this was, well, the Babylonians paid attention to the sun, and the sun appeared to them to move every day just a little bit. And after a full year, well, the sun appeared back in its original position. And this is where the year comes from. It's that, well, it's what appears to be the sun moving around and then eventually ending up in its original position. And that's forming a full year. And they wanted to be able to describe this movement in a precise way. And so let's say that the sun appears to move in a circle. So if we imagine that they were like, well, if we have a circle and we decide to, well, we notice that the sun appears to take about 365 days to end up in its original position again. So what if we approximate that and say that, well, in a circle there are approximately what we could call degrees and 360 degrees. So we divide this up into 360 degrees, and that would mean that, well, right here we're at 0 degrees, right here we're at 90 degrees, this would be 180 degrees, this would be 270 degrees, and this would be 360 degrees. And that would be nice because, well, as the earth is moving, the sun appears to move eastward just a little bit every day. And so we can imagine, let's draw this out. And then let's say that the earth moves right here. And let's say that that was the movement for 1 day. And so if we kind of draw out this angle here, not the best, but let me do this instead. Then it's going to form this angle here of what the sun appears to move. Because if the earth is moving this way, right, the earth is moving like that, and you're looking at the sun appears to move a little bit eastward. And if we use the circle as being 360 degrees, then we could say that for each day, the sun moves approximately 1 degree per day. And that would make things very convenient. And furthermore, if we, instead of saying exactly 365 degrees for a circle and use the 360 degrees, then we can still say that the sun moves approximately 1 degree per day, but then we can also have that the circle can be easily divided up because 360 is a number that's very divisible. And for example, more compared to 365, because 1/4 of 365 is not going to be a whole number like 90 degrees is. And so 360 degrees lets us approximate 1 degree per day, and is a number that is very divisible. And that is ultimately why we think that the Babylonians may have chosen the 360 degree circle. Although the exact reason is unknown, this is our best guess as to why the 360 degree circle was originally formed. Now, the point here is that the degrees don't really have any true geometric meaning to a circle. The choice of 360 degrees to represent the full amount of, or the angle measures in a circle, is very arbitrary. We could have just as well chosen and say that, well, let's say that a circle is, instead of 360 degrees, let's say it's 500 degrees. And then 1/4 of that, or I'm sorry, not 500, let's say it's 400 degrees. Then 1/4 of that, we'd have 100 degrees here. We'd have 200 degrees here, 300 degrees here, and then the full circle would be 400 degrees. And it could have just as well been that. Had it not been maybe for something else like them trying to track the sun or something. But that's the thing, is that it's very arbitrary and doesn't have any geometric meaning. And this kind of became an issue. And so mathematicians wanted to try and come up with another form of angle measure that does have a geometric meaning. And that is where the radians comes into play. So the radians, if we notice here, let's draw a circle. Now, as I said earlier, there are 2 pi radians in a circle. So if we start here, we're at 0 radians. When we're 1/4 of the way, this is going to be pi over 2 radians. This is going to be pi radians. And this is 3 pi over 2 radians. And all the way around is 2 pi radians. And one thing we might notice here is that if this is a unit circle, and a unit circle meaning a circle with a radius of 1, and we were to try to find the circumference of that circle, well, the formula for circumference is C equals 2 pi r. So if we have a unit circle, meaning the radius equals 1, then the circumference of that circle is equal to 2 pi. And that is the key here. The key is that the radians is truly just a measure of the circumference of the or of the unit circle. And so this 2 pi radians is this circumference if this is a unit circle. So for example, also, if we just go from here, we take this segment of the circle from right here to here, then the length of that segment of the circle, the length of that arc, if it's a unit circle, right, the radius is 1, then that length is going to be pi over 2. And that is the exact length of that arc. It is not arbitrary. It has a true geometric meaning. And that goes for all of these, right? From here to here, the length of this arc is pi. It is exactly pi, right? And again, I just want to remind us that's when we're using a circle with a radius of 1. But if we have a circle with a larger radius, right? Let's imagine we have a circle down here, and the radius of the circle, so let's just draw kind of an angle here. Let's say that this is like so, and the radius of this is 5. So it's a circle with a radius of 5, and let's say that this angle formed here is pi over 4 radians. That, let's see, is pi over 4 radians. And we want to find the length of this arc right here. Well, because we're using radians, all we would need to do to find the length of that arc is, well, arc length equals radius times theta. And theta is just means the angle measure. And in this case, our angle measure is pi over 4. And our radius is 5. So the arc length is 5 pi over 4. But we can only use the formula in that way if we're using radians. If we were to instead use degrees, we would need a conversion factor of, so let's say instead, let's have this here. Let's say this is that, and that, this is 5. And pi over 4 in radians is equal to 45 degrees. So 45 degrees. And if we want to find the arc length of this, that's going to equal r times theta in degrees times, well, we need to convert from degrees to radians, so we're going to need the conversion factor of pi over 180. And that is how we'd find the arc length of this. So we can already kind of see here that working with radians makes our calculations a bit easier. We don't require any kind of conversion factor because the radians has a true geometric meaning as opposed to the degrees kind of just being arbitrary. And one further example of how the radians is more useful or more efficient to use than degrees. If you haven't taken a class on calculus, that's fine. But just to kind of throw this example out there and to let you see, in calculus we have something known as a derivative. And we can take the derivative of the different trigonometric functions such as sine, cosine, tan. And if we look at the derivative of sine of x using radians, then the derivative is just going to be cosine of x. But if we take the derivative of sine of x and we're using degrees, then the derivative, we're going to have to bring in the conversion factor, and it's going to actually become pi over 180 times cosine of x. And these kind of conversion factors will pop up everywhere, making calculations less efficient. So I hope that at this point you have a better idea of the difference between degrees and radians and why we might want to use one over the other. That is going to wrap up today's video, and I would like to end with just a fun fact from philosophy. Did you know that within philosophy there is a famous problem known as the mind-body problem? And this problem basically goes along the lines of how can a mind, which is something that is immaterial, interact with a body, which is something that is material? And yeah, so that's just something to think about. And if you enjoyed this video, please be sure to like and subscribe. That really helps out.